Okay, so I just want to make sure everybody has everything they need for this worksheet. There were a couple problems we didn't have to do because we hadn't covered friction yet. I'm at just some of the basics here to start off with, like converting these two fractions. If you recall from 2 weeks ago, there is a difference between converting to an exact fraction and converting to a fraction to the nearest eighth inch, 16th of an inch, or whatever unit we're looking for. So for the first set here, we want to an exact fraction. So like 0.8125, make that 8125 over what is the denominator? 10,000. You got it. That's the tenths, hundredths, thousandths, 10,000ths. Again, the shortcut, if you want to double check, there's 4 decimal places. There has to be 4 zeros in that denominator. Now, of course, we have to reduce that. Both of those can be divided by 125 will work. 8,125 divided by 125. 65. 10,000 divided by 125 is 80. And of course, both of those can still be divided by 5, giving us 13/16. Did something go wrong?
I thought I wrote 1 3/16.
Oh, gotcha. Okay. Perfect. So for part B, 0.125 is going to be 125 over 1,000. Both of those are divisible by 125. If you didn't see it, you could have divided by 25 or 5 and just kept going. You will get to 1/8. That one, hopefully 0.125, you're getting to the point where you just start recognizing that as 1/8. The 0.8125 is 13/16 is a little bit more of a stretch. But at some point, if you ever talk to like an old machinist or old mechanical designer, I know almost all of them have all their decimals memorized down to a 16th, but I know a couple that have them down to a 64th. I don't have them down to a 64th, by the way. So see there, the one in front we're just going to ignore for now. Then of the 1,875 over 10,000. And both of those can be divided by, well, we know they can both be divided by 25, right? So 1,875 divided by 25, what is that, 75, I believe? Over 400. And then they can both still be divided by 25. 75 divided by 25 is 3 and 16. And then we can't forget the 1 that we left off. That is 1 and 3/16. So that one is 1 and 3/16.
Yeah.
So then the next one, 4,375 over 10,000 again. Well, I'm pretty sure they can both be divided by 125, so let's go with that. 4,375 divided by 125 is 35. 10,000 divided by 125 is 80. And once again, they can both be divided by 5. Giving us 7/16. Any questions on those first 4? Okay. The next 4 here for problem 2 is just converting to an exact decimal. What's the process of doing that? You got it. 3 divided by 8. We looked at how you could divide that out by hand, but we have the calculators. No use wasting the time doing the long division. That's 0.375. Does anybody have a calculator that when they punched that in, it kept wanting to give it back as a fraction? No? Okay. It's usually just a mode setting. If you have it in math type setting, every time you do it, it'll give you a fraction, and you have to have it in linear or standard mode. Yep. So 3/4, 3 divided by 4 is 0.75. 13/16, 13 divided by 16. 0.81. 625, isn't it?
Yep.
I don't know why I wanted to say 7.5 there for some reason. And then 1 1/16 is 1.0625. If you thought it said 11/16, that would have come out to what? 0.6875? Yeah. Sure. Yeah, that is supposed to be 1 1/16. So you take the 1 off of it, keep it separate, just do the 1 divided by 16 to get the 0.0625, and then you put the 1 back in front. Number 3 here is one that comes up more often than you would think. So you have a calculation where you're working with the decimals, but you need to match it to a tool size, and your tools go to either the 64th or sometimes the 1/28th if you have the really expensive tools. We need to match it to that. So to get these to the nearest 64th, it is a totally different process than what we did for the exact fraction. We keep it as a decimal, 0.399, and we put it over 1. Then what do we do? You got it. Times 64 over 64. Technically, that 64 over 64 is equal to 1. So what we're doing is we're doing a conversion here. We're changing the appearance, but not the value. So 1 times 64 is 64. The 0.399 times 64 gives us 25.5. Really, all I need is the first digit after the decimal there. 25.5 is going to be between 25 and 26. It's closer to 26 64ths. So that'd be 13/32 of an inch. Any questions on that one?
I didn't know if you wanted us to reduce it or not.
Typically you would, because your tools will be, it's still to the closest 64th. It's just reduced, simplified. Yeah. Yep. If you left it as 26 64ths, I wouldn't mark that wrong on a quiz.
Yeah.
But if you're thinking about a toolkit,
Yeah.
you're going to have reduced fractions on your tools. If you ever want to take somebody and drive them nuts, somebody that's not good with math, take a socket set, pull out all the sockets, dump them in a pile, and tell them to put them back in order. And you watch somebody. It's a great math exercise, actually, but you frustrate the heck out of somebody that's no good with fractions. Not that I mean enough to have ever done that.
I don't believe, again, that's why
I actually have a friend's son who struggles with fractions, and I've done that to a couple of times. Go ahead, put these back in order. Or I'll pull a couple of them out and, which one's bigger, which one goes where.
That's pretty simple like this here.
Oh, I'm pretty sure he's going to show up at my house and smother me with a pillow in my sleep one of these days, but at least he'll know his fractions. So anyway, here we're going to multiply by 64 over 64 again. The 0.777 times 64. 49.7, which rounds to 50. You got it. And of course, we'll reduce that to 25/32. When we hit the decimal down here, 1.29, again, we ignore the 1, take the 219, I should say, over 1, and we'll multiply by 64 again. 0.219 times 64, 14.0. So that's 14/64, or 7/32. And we have to remember that 1 in front of it, the whole number. Of course, that's inches. And finally, the 0.5803 over 1 times 64. We're at 37.14, which is closest to 37. So that's just 37/64 of an inch. Any questions on any of those? Okay. So 4 and 5 are the friction ones that I said we didn't have to look at. We'll come back to those later, actually. Belt length. So we have to remember our formula for belt length. Now remember, we said that if the pulleys are really close to the same size, there's a much simpler formula. These are probably just far enough apart with 3 3/4 and 5 1/2 that we might have to account for that difference. Let's do it both ways and see how it comes out. So the long formula is that length equals 2 times C, which is the center to center distance. That'll be the 16 1/2, plus 1.57 times D plus D. So big D is the 5 1/2. Little d is the 3 3/4. And then plus big D minus little d, so 5 1/2 minus 3 3/4 squared divided by, and I always put the extra set of parentheses in here, 4 times C, so 4 times 16 1/2. Fortunately, this can be done on our calculator. And fortunately, all these numbers are real easy to convert into decimal. 2 times 16 1/2 is just go 2 times 16.5 plus the 1.57 times my parentheses. 5 1/2 is just 5.5 plus 3 3/4 is 3.75. Good. Close the parentheses. Plus, now in parentheses again, 5.5 minus 3.75. We have to close the parentheses and square that. And then divided by, got parentheses, 4 times 16.5. We get 47.57 inches if we round it to the nearest hundredth of an inch. Now, what if we didn't account for the fact that the pulleys were different sizes? What we would have done there is we'd have just used that first part of the formula without that correction factor. This part is the correction factor for the fact that it's not going, the small pulley is not going the full half diameter, the large pulley is going more than half the diameter, and it's an angle, so it's a slightly longer than just the center to center distance. So if we just did that, 2 times 16.5 plus 1.57 times 5.5 plus 3.75, we have 47.52. So here's a case where those pulleys, 3 3/4 and 5 1/2, were close enough that it really did not make a difference whether we use the full formula or just the shortcut formula. The correction for the angle, the pulleys being different sizes, was literally 5/100ths of an inch, less than a 16th of an inch. We're probably, your belts come in sizes, what, to a 1/2 inch? I don't think they even come down to a 1/4 anymore, do they? Yeah. So, I mean, you're going with a 47.5 inch or a 48 inch belt and you're adjusting it to fit. So. Number 7 then, same thing, finding the belt length required. So 2 times, you tell me what to put in here. 17.6 plus. Okay. Plus, in the parentheses, 4.2 minus. Perfect. Now, I get asked all the time, does it matter what order you put these in here? Technically, yeah, it does. But when you do the calculation, you're going to square it. So 4.2 minus 2.8 would be a positive 1.4. Squared, that's 1.96. If you did it backwards, you get a negative 1.4. When you square it, it's still 1.96. So in this case, because it's squared, it doesn't make a difference, but you should get in the habit of always putting the bigger one first. So 2 times 17.6 plus 1.57 times 2.8 plus 4.2 plus 4.2 minus 2.8 squared divided by 4 times 17.6. 46.22. Again, let's just double check. Let's see if that's a big enough difference in diameter to make any real difference here. So 2 times 17.6 plus 1.57 times 2. Thank you. .8 plus 4.2. 46.19. So again, that's actually less than a 32nd of an inch difference. So to be totally honest, unless there is a major difference here, that's 50% difference from one pulley to the next, and it still didn't really make much of a difference in our belt size. Unless there's a huge difference between the belts, that portion of the formula without the correction factor is generally enough to get you an approximation. Because all these calculations are approximations and you're adjusting to fit anyway. Any questions on either of those two? Okay, so we're going to properly tension a belt. If we have the 3 3/4 inch pulley and a 5.5 inch pulley, the centers are 16.5 inches apart. How do we figure out our proper deflection? It's L over 64. What is L? The centers. You got it. So 16.5 over 64, which is going to give us like 0.258 basically. So when you press on that belt, do you guys know what we're saying when we say deflection? Yeah. Just press on the belt with, I've never actually seen the exact amount of force. I'm just not going to lean on it, but generally the belt, even if you press really hard, it shouldn't go much more than a 1/4 inch away from its normal path. Have they given you guys an exact amount of force for that? No?
Yeah.
Have they?
We have some stuff. Yeah, we have like a weird tension meter. We actually go underneath the
You
belt.
hang on it?
Yeah, you
Yep.
hang on it. Belt stops moving.
Okay.
So,
Yeah, I didn't know. I've never seen it in a book anywhere that says you apply so many pounds of force to it or anything.
yeah, you actually like pull up on it to actually see on the non-tension. On the,
And it has a gauge where the spring pulls into that gauge,
yeah,
so you know you got the right tension.
style weight scale.
Yep. It's called a go no-go gauge. So when it's in the range, you've got your acceptable.
Pretty much.
Sure.
Yeah, I think they asked for like 8 thou or something, or not 8 thou, 8 millimeters.
Okay. Cool. So V belt that has a 24-inch span, that'll just be 24 over 64, which we can divide out. 0.375, of course, that is 3/8 of an inch. If you're okay, so find the size of a driven pulley needed if there's a 3.5 inch pulley on the motor. So the 3/2 inch pulley, remember this pulley ratio is the diameter of the driven pulley over the diameter of the motor pulley or the driving pulley. So we have a 3.5 inch pulley on the motor. We're looking for the size of the pulley that's going to be driven, and we need a 10:7 ratio. So we're going to cross multiply and divide. 3.5 times 10 divided by 7. What does that give us? 5 inches? Find the RPM of a 6 3/4 inch driven pulley if it is connected to a 4.5 inch pulley going at 900 RPMs. Now again, your book gives you this formula that says the RPM of the driven pulley equals the diameter of the motor pulley times the RPM of the motor pulley over the diameter of the driven pulley. Really simple. All it is, the formula is always the same. And they give you that different formula no matter for each different thing that could be missing. If you're looking for a missing diameter, missing RPM for the motor pulley, whatever. The simple formula that's always going to be the same is it's the diameter of the driven pulley times the RPM of the driven pulley equals the diameter of the motor pulley times the RPM of the motor pulley. You don't even need to call them driven and motor. You can call them pulley 1 and RPM 1 if you want to. So that means that all we're going to put in here for the driven pulley, it is 6 3/4. I'm just going to put 6.75 times that missing RPM equals 4.5 times 900 RPMs there. To solve that, we multiply 4.5 times 900, and then we divide by the 6.75. So we get 600 RPM on that driven pulley. Any questions on that one? Or on those two? And again, the reason this setup works here, up here we had to do a proportion with the two fractions and cross multiply and divide, because that's what we call a direct relationship. One number gets larger, the other number has to get larger. Oops. This is called an inverse relationship here, because when the size of the pulley gets larger, the RPM gets smaller. So that's why it is set up as the two numbers multiplied by each other instead of divided by each other in a ratio or a fraction. If you get in the engineering side of things, obviously that's my side of things, knowing direct relationship and inverse relationship is a big deal, because there's a number of problems you can solve if you don't remember the formula just by remembering the direct or inverse relationship and doing exactly what we just did there, either setting up a proportion, cross-multiplying and dividing, or setting up that simple equation and solving it for the missing piece. Number 12, find the size of the driven pulley needed if the radial speed of 550 RPMs is required and is being driven by 2.75-inch pulley at 800 RPMs. This is just exactly the same type of question with different numbers. It doesn't matter which one we put first, so I'll put 2.75 inches times 800 RPMs equals X inches times 550. And again, we'll solve it by multiplying those two and then dividing by the 550 to solve for X. 2.75 times 800 divided by 550. That is 4. So that's a 4-inch pulley that's required there. Okay, so now we're moving on to torque. Find the torque applied if there's an 80 pounds applied to a 3-foot lever arm. So you just multiply the force times the length of the lever arm. 80 times 3 is 240. And your book calls it pound-feet, doesn't it? Pound-feet or foot-pounds are the same thing. It just depends on what textbook you're using, what order they put them in. Find the maximum load that can be lifted by a motor capable of 300 foot-pounds of torque, turning an 8-inch diameter pulley. Now, there's a reason I underline diameter, because if the diameter of the pulley is 8 inches, the moment arm is going to be 4, half of it. Because if that's the pulley, 8 inches of the diameter, the moment arm is just from the center out. That'll be 4 inches, just the radius. So the torque is 300 foot-pounds, but this is in inches. The 4 is in inches. So we're going to convert that torque into inch-pounds. 300 foot-pounds times 12 inches over 1 foot. You got it. So the feet will cancel out. 300 times 12 is 3,600. Pounds times inches will be pound inches now. So then now we can calculate the maximum load it can lift, because that 3,600 pound inches is going to equal to our load in pounds times 4 inches. To solve for X, we do what? Divide by 4. I don't need to write that out. That's just going to be 900 pounds. How many of you got that one? How many of you didn't miss the conversion by 12? Okay. Anybody have any questions on that? 15. Find the available torque supplied by a 2.5 horsepower motor at 1800 RPM, round to the nearest tenth. I put tenth of a horsepower, but that's our available torque is that magic number 5252 times the horsepower, so 2.5 horsepower, over the RPM. So 5252 times 2.5 divided by 1800 gives us 7.29. You gotta keep remembering it's pound feet in your textbook, not foot pounds. So then now there's all sorts of different combinations or variations of this. Find the operating RPM. If we have 9 foot-pounds of torque or 9 pound-feet, so 9 goes in for the torque now. 5252, the horsepower is 2 1/4, so 2.25. And we're looking for the RPM on bottom here. If you recall the strategy we talked about, if you're looking for a number that's on the bottom of a fraction, is to turn it into a proportion. So you put this number over 1, now it's a cross multiply and divide. So you multiply this direction and divide by the 9. So the first thing we have to do is combine the 5,252 times the 2.25. We get 11,817. Then we'll multiply by 1 and divide by 9. Well, multiplying by 1 doesn't do anything, so we just divide by 9. We get 1,313 RPM. So that'd be the operating speed for that. How many of you had that one? Good, that was a tough one. Any questions on that one? So that is the trick. Whenever you're solving for something in an equation, and what you're solving for is on the bottom of a fraction, that is generally the easiest way to do it, is to turn it into a proportion so you can cross multiply and divide. Find the horsepower required to supply 450 foot-pounds of torque at 520 RPMs. So we got 450 for torque, 5,252 times the horsepower over 520 RPMs. So here we can just solve this. We're going to take the 450 and what are we going to do over here to get rid of stuff? Well, to get rid of the 520, we have to multiply. So multiply by 520. That'll cancel that out. So 450 times 520. Then we have to get rid of the 5,252. To get rid of that, we will divide. You got it. So we'll divide by the 5252. So divided by 5,252 gives 44.55. Horsepower. Probably round that to 44.6 horsepower. Okay, so find the horsepower required to turn a wench with a 6-inch diameter drum at 4 RPM to lift a 1,200-pound load. So the first thing we need to find here is the torque. How do we find the torque? £1,200 is our load. What's our arm here? Our moment arm? 3, half of the 6-inch diameter. Now that is in inches, so we have to divide by 12. Perfect. So 1,200 times 3 over 12 is 300 pound-feet of torque. So that's the required torque. Now we need to find the horsepower. Well, it's the same formula we're using up here. It is the torque, 300 pound-feet, equals 5,252 times the horsepower over 4 RPM. times both sides by 4, so 300 times 4. And then divide by the 5,252, we get 0.228. So a quarter horse would do that one. Any questions on that one? Oops, I'll leave it up for a second for you. Okay, so then moving on, find the number of teeth required for a driven gear if we need a 5-to-4 gear ratio. So 5-to-4 gear ratio. If the motor, so remember it's the driven gear over the motor gear. So the 24 teeth for the motor goes on bottom. We cross multiply and divide. 5 times 24 divided by 4 gives us 30 teeth on the driven gear. Find the RPM of a 32-tooth driven gear interacting with a 48-tooth gear running at 900 RPM. This is just like the pulleys, only instead of diameters, we have the number of teeth. So this is 48 teeth times 900 RPM equals 32 teeth times whatever that RPM is going to be. So where do we start? 48 times 900, and then divide by 32. Giving us 1,350 RPM. Next, find the number of teeth required in a driven gear if the machine needs to operate at 2175 RPM, is connected to a 1,450 RPM motor with 33 teeth. So 33 times 1,450 equals however many teeth this is going to be, times 2175. What's my calculation? 33 times 1450 gives me 47,850, and then divide by the 2175, giving us 22 teeth. Questions on those? Cool. So here we're going to find the RPM in that final driven gear. So we start off here, 40 teeth at 900 RPMs, turning that 12-tooth gear. So 40 times 900 equals 12 times, we're just going to call that R for RPM. Tell me what to do. Perfect. 40 times 900 divided by the 12. We get 3,000 RPMs there for that idler gear. So that's 12 times the 3,000 equals 60 times that RPM. We'll just call that R again. So 12 times 3,000, and then divide by 60. Gives us 6,000 RPM. Look right there.
No, you forgot your 0. You just divided by 6.
Ah, there we go. So 600. Thank you. Has more teeth, it should be turning slower. Idler gears, one thing to remember, idler gears there do not affect the speed of the final gear. The speed of that, the RPM of that final gear, I could have just gone directly from the first gear. 40 teeth times 900 RPMs equals 60 teeth times whatever that RPM is. 40 times 900 divided by 60 gives us 600 RPM. So it's kind of a quirk of gears that the idler gear really does not affect the relationship at all. The only way the idler gear affects the relationship is if we have a gear hitting an idler, and then that idler is actually on a shaft with a larger gear or another gear, and then they interact. Then you have to get the RPM of this middle one, and then you've got to go to the other gear. It doesn't happen near as often with gears as it does with pulleys. Hence this next example. So here we do have to consider that center connection there. That is 2 pulleys on a shaft My artwork really sucks there, but hopefully you guys are able to get the picture. So we find the RPM of this middle pulley. We have an 8-inch pulley times 800 RPM equals 5-inch times whatever that RPM is. So where do we start? 8 times 800 and then divide by 5. So we get 1,280 RPM there. Now to go to the next pulley, we use the 6-inch pulley times the 1,280 RPM because they're on a shaft. The 5 and the 6-inch pulley will have the same radial speed, same RPM, equals what? 4 times whatever that RPM is. So what do we do? Then divided by 4. Good. 1,280 times 6 divided by 4 gives us 1920. Any questions there? So because there were 2 pulleys here connected on a shaft, it did affect the final speed. Gear pitch. Anybody remember the formula for gear pitch? Teeth over the pitch diameter. You got it. So 28 teeth over 4 inches is a pitch of 7 or 7 teeth per inch if you want to put units on it. That is your gear pitch. The importance of gear pitch, of course, is gears can only mesh with each other if they have exactly the same pitch. There's a whole ton of formulas I could go through with spur gears, but we're not going to get into them. Maybe when you guys get to the semester on machining, we'll look at that a little closer. Any questions on any of these off the worksheet? Okay, well, let's get a quiz at you. For those of you that are new on the quizzes, you can use your worksheet, you can use your notes, you can use your book, any resources you want to use except for your neighbor. If you have any questions, let me know.
That's one reason why I sit by him.
If you're right today, maybe just
So, what section was
in the book, it was chapters 8 through 12, I believe.
You definitely made a mistake.
What'd I do?
Take a look at that.
I was like sitting here for a second going, I forgot that I put that as the first page in here. Thank you. To be fair, the way it was printed, you couldn't have turned it back in without me noticing.
Oh, I know. That's why I was super confused.
Sorry about that. Eight through 12, I believe, yes. This is the same thing. Oh. Let's see here. There you go. You bet. You took the right copy here. Thanks, man. Hopefully. Look at it before I hand it to you this time. That one should be right. Thanks.
You know, you can just borrow me one of those answer keys.
For the right price, make checks payable to the Todd Huff Retirement Fund.
I'm more of a cash person.
Just kidding. I don't take checks. I would accept a healthy kidney of the right blood type. I wish I was kidding. So we'll start off with that concept on the first worksheet. There was questions 4 and 5 that we didn't do last time around because they're dealing with friction and we didn't get to friction. So friction, you obviously all know what friction is. It's the resistance caused by two surfaces sliding past each other. And we deal with friction, there's two types of friction. There's static and kinetic. Static friction just means it's sitting still, and kinetic means it's moving. A lot of people don't realize, but two objects that are sitting with zero motion relative to each other, in other words, sitting still, have more friction between them than when they're moving. I don't know if you've noticed, if you're dragging something across the floor, it can be really rough to get it moving, but once it's going, it pulls a little bit easier. And that's exactly a scientific truth, that it is true. Once it's moving, friction is less. Part of it is because bonding between particles. So the force of friction is equal to something called the normal force times, we usually use the letter mu, which is a coefficient of friction. Normal force is the force perpendicular to the surface. If we're on a flat surface, it's just the weight of the object. If it's an angled surface, it's the portion of the weight that is, if we're on an incline like this, it would be the portion of the weight that is perpendicular or at a right angle to the surface of the incline. So looking at the first worksheet there, number 4, find the force of friction on a 280-pound object dragged across a flat surface. We're assuming flat means level as well, where a coefficient of friction is 0.09. So the force required to overcome that force of friction is the normal force, 280 pounds, times the 0.09. 280 times 0.09 is 25.2 pounds of force that would be required to drag that.
I don't think we have the right worksheet.
This is still back on worksheet 1.
Oh, gotcha.
Yep.
Sorry.
These are those 2 problems from worksheet 1 that we didn't have. Next is number 5 from worksheet 1. This one we actually break it down the difference between static and dynamic or kinetic friction. So here we have a 350-pound object, again sitting on a horizontal surface. Static friction, static coefficient is 0.18, and the kinetic or dynamic is the word I used in that. I guess that's what your textbook uses, dynamic friction, is 0.11. So A is asking the force required to start moving the object. Start moving the object would be static friction if it's starting out moving still. So that's the 350 pounds times 0.18 gives us 63 pounds of force to get it moving. Then part B, to keep it moving, would be the 350 pounds times that dynamic coefficient of 0.11, which is only 38.5 pounds. Before I move on, I do want to discuss one little thing about friction. What are some methods that can be used to reduce the force of friction? A lot of people will say, well, lubrication. Lubrication is the main way in manufacturing that is done. Lubrication actually creates a film so that the 2 surfaces aren't actually riding against each other. What happens is a good lubricant actually serves as like little balls. We've all done it where you put pipes under something to roll it across the floor, or small ball bearings. And that's what it is rather than the 2 surfaces rubbing past each other, that liquid viscous lubricant actually kind of rolls in little balls between the 2 of them. That's why too thin of a lubricant doesn't do any good, because it doesn't have any substance there. The second thing that people do is polishing. I spelled that wrong. There's 2 L's in polish, I believe. If you polish something, make the surface smoother, it works to an extent. Obviously, if I have surfaces that look like this, rubbing up against each other, there's going to be a lot of friction. It's not just friction, it's actually mechanical resistance because they're going against each other. Polishing actually does not reduce friction, it reduces that mechanical resistance. You do want smooth surfaces. I mean, you don't want, if you have a shaft that has a surface that's the consistency of sandpaper, it's going to grind away at any sort of bushing that it's turning in. Not good. But, so you want to have it polished enough that it eliminates the mechanical resistance, any sort of binding interaction, any intertwining between the surfaces. Polishing itself, though, again, once you've eliminated the mechanical resistance, does not reduce friction. In fact, it can cause other problems. You guys ever worked with gauge blocks? Anybody? A couple of you? Gauge blocks are very, very finely machined blocks that are used to create precise heights if you need to create angles or whatever. The surface on the gauge blocks is very highly polished. Have you ever wrung the gauge blocks? Yeah. So if you take them and you rub them together, they'll hit a spot where it's almost impossible. You really have, you'll break fingernails trying to pry them apart because the surfaces are so smooth they actually bond together. So if you get surfaces too smooth, you can have ringing between the surfaces where they literally will not come apart. As long as the surfaces keep moving, it's not a problem, but once they stop, it can be really difficult to get them started moving with each other again. Yes. Yeah, those they either have to have them lubricated so they're not dry, or you have to keep it moving because once it stops, it takes a lot of force to get them going again.
We have ceramic valves, like electronic controlled valves.
Yep.
You actually take apart, and I tell you what, you just pop fingernails off trying to get them separated.
And that when those fail, it's usually not while they're moving. It's usually once they've stopped and they start moving again. Yep, that's usually the failure on those. Okay, so now we're moving on to the second worksheet here. So this is worksheet 1B. So our first topic here on the second part is thermal expansion. So thermal expansion, obviously things get hot, they get bigger. We've all known that from a young age. When we talk about materials, metals, and other materials, there's a very predictable rate of expansion. So that little triangle there is called delta. It signifies change in a characteristic. So delta L is change in length. So the change in length for a material depends on the original length of the material. Delta T is the change in temperature. And C is a thermal coefficient. Technically, it's the thermal coefficient of expansion. So for this example here, number 1, we want the new length of a shaft that starts out 60 inches long. So that's our original length. At 80 degrees Fahrenheit, operating temperatures increase from 80 to 140. What's the change in degrees there? 60 degrees. Coefficient of expansion is 0.0000075. Now, a lot of times you won't see a coefficient of expansion written out like that. I wrote it out like that because I didn't want to spend a lot of time going through scientific notation. But most of the time in a manual that you're looking up, you'll probably see that written as 7.5 times 10 to the negative 6. What the negative 6 means is you take that 7.5 and you move the decimal point 6 spots to the left. So you got to fill in zeros. There's your decimal point. So 0.0000075. Is there anybody that's not seen scientific notation before? No? So that is the biggest thing. Most of the scientific notation you'll see will be with that negative number. And that negative number after the 10, as the power on the 10, that's how many spots you have to move the decimal point to the left. So if we have 2.8 times 10 to the negative 4, that means you take your 2.8 and you move that decimal point 4 spots to the left. So 1, then I have to add a 0 for 2, 3, and 4. That's where your decimal point is, 0.00028. So again, typically your coefficient of thermal expansion will be written out like that in scientific notation. I put it out as a decimal just to make things a little quicker for us here. So as we multiply that out, I think that comes out, what is it, 0.027, I believe that'll come out to, if we multiply that out. That is the change in length. We asked for the new length, so what more do we have to do there? Yep, 60 inches original plus the 0.027 inches. It is now 60.027 inches. Doesn't sound like a significant change, does it? Doesn't sound like much. On a 60-inch shaft, it isn't much. It's less than a 40th or about a 40th of an inch. If you're dealing with longer things, a roof truss, thermal expansion on a roof truss can be as much as a half of an inch. That'll actually cause 7 or 8 inches of rise or fall in a roof if you have radical temperature swings. The bigger thing is bridges. You ever see in bridges, you're driving along and you have that like 2-inch gap where you have these metal plates? Those are expansion joints. Bridges will expand. Again, 8 to 12 inches, depending on the structure and the length of the bridge. Without those expansion joints, those bridges would actually heave up 2 or 3 feet in difference from where their normal elevation would be. It's really amazing. That's why you see concrete, really hot sun, or the pavement on the roads, the blacktop will have big busts because it'll actually expand enough it'll heave up and crack through. Find the maximum operating temperature if an oil pan is 18 inches long at 65 degrees and is allowed to expand to a length of 18.0117 with that coefficient of expansion. So here what we're looking at is how much expansion do we have to get from 18 inches to 18.0117? 0.0117. That's our change in length. The original length was the 18. We are looking for the change in temperature. So that's that delta T. and our coefficient of expansion, 0.0000065. So we're solving for delta t. We're going to start with the 0.0117. What do? Well, we'll divide by the 18 and by that coefficient of expansion. So we'll start out dividing by 18. Then we'll divide by the 0.0000065. We get 100 degrees. That is not the maximum operating temperature. That is the change in temperature from 65 degrees plus 100. It can go up to 165 degrees Fahrenheit. I get asked occasionally when I do this, how do we know whether temperature is measured in Fahrenheit or Celsius? You'll actually know when you look at this constant, because it'll actually be, technically it'll be, well, let's write it out. It'd be written as like 0.65 times 10 to the negative sixth inches per degree Fahrenheit, or centimeters per degree Celsius, or millimeters per degree Celsius, depending. So you look in the units and you can see what type of temperature, what type of length measurement is being used in that thermal coefficient. Next, we're going to talk a little bit about scale drawings. So scale drawings are just a ratio, a proportion like we saw earlier. Here, we have a scale that is 1/2 inch equals 1 foot, so that's 1/2 inch to 1 foot. The actual length of the object is 24 feet, so we put it in here. The biggest thing with these proportions is you have to make sure the units match up. This is feet and that's feet. This is inches. This is going to have to also be inches. So we cross multiply and divide. 1/2 times 24 is 12, divided by 1. So when that is drawn, it'll have to be drawn at 12 inches long. So the second one here, we have a scale of 1/8 inch equals 1 foot. This is probably your most typical layout scale if you're doing any sort of architectural drawings or a floor layout. Occasionally you see 1/4 inch equals 1 foot, but you'd have to have a fairly small. What 1/4 inch equals a foot is more used for like a residential, a house. You get into a manufacturing setting, it wouldn't fit on a page if you use the 1/4 inch scale. So again, we have to make sure we match up. The actual length is 18 inches. Well, the 1 foot represents the actual length, but now we have an issue. These units are not the same. So we either have to change the 18 into feet or the 1 foot into inches. Easier to change the 1 foot to 12 inches. So now those have the same units. And now we can go ahead and cross multiply and divide. 1/8 times 18 divided by 12. I believe that comes out to 3/16 of an inch. Or 0.1875 if you're using decimals. This one's going the other direction. If we have the scale and the drawn length, we want to know the actual length of the object. So if our scale here is 1/2 inch equals 1 inch, or 1 foot, 1/2 inch equals 1 foot, equals the 3/4 inch is the drawn. That goes on top. Those do have the same units of inches. So we'll cross multiply and divide. 1 times 3/4 divided by 1/2 is 1.5. That's 1.5 feet, not inches, 1.5 feet long is the actual length there. Here we have a 1/4 inch equals 1 foot. And we've got a drawn length of 2.5 inches. Cross multiply and divide. 1 times 2.5 divided by 1/4 is 10 feet long, I believe. Anybody need me to go back and do those calculations more slowly? Okay. Next, we're looking at linear speed versus radial speed. We're used to seeing radial speed in RPM, which is one way to express it. But we also then have the linear speed of the outside of the surface. If we're looking at a pulley, let's say we're looking at a 4-inch pulley, the radial speed or the linear speed of a point on the surface of that pulley is also the linear speed of the belt that would be turning on that pulley, is how far that point goes in inches around that pulley as it spins. Well, first we look at one rotation of the pulley, or in other words, the circumference of the circle. Anybody remember the formula for circumference of the circle? Pi times 2r or diameter. So it's either pi times diameter or 2 pi r. Either one works. Dealing with pulleys, we typically know the diameter, so we're going to use that top one. So the distance around the pulley once is, we're just going to use 3.14 for pi, times the diameter of 4 gives us 12.56 inches. But it's not just turning once, it's turning 1,600 times per minute, 1,600 RPM. So we'll multiply that then by 1,600. Oops, got my one in there. Giving us 20,000 inches. Speed is usually not measured in inches per minute. It's usually measured in feet per minute. So this is inches per minute right now. How do we convert that to feet per minute? Divide by 12. Giving us 1,674.67 feet per minute. Why did I put in 4 in there? That should have been 8. Okay. Yep, it does. So this ends up being 40,192 divided by 12, which will be 3349. The reason I was able to do that calculation so fast is 8 is just doubling it, so I'm just doubling everything. Helps if I actually read the problem before I start doing calculations. Sorry about that. That would make this times 8, so this would be 25.12 inches as well. So number 6 asks us to go the other direction. How many RPM do you have to go if we want to get a linear speed of 18 feet per minute? So we have 18 feet per minute. It's going to be 3.14 times the diameter of 7 inches. I'm going to put the 7 over 12 to convert it into feet. Times, we're going to put R in there for RPM. So again, we're solving for R. So we start with the 18 feet per minute. To get R by itself, we have to divide by 3.14. And then we have to divide by the 7/12. I have to put the 7/12 in parentheses because I don't have fraction function on this calculator. Gives me 9.83 RPM. So that's not turning very fast. Most winches turn at like 50 to 150 RPM. So now we want to combine some of the stuff from the last worksheet where the torque created, capability of the motor, all of that come into play. So we're looking at a 4-inch diameter winch. We want to lift a 900-pound object at a speed of 12 feet per minute. So to solve this, the first thing we need to know is the required RPM, which is what we just did up above. So we have 12 feet per minute equals our pi, 3.14, times our diameter of 4 over 12 to make it into feet, times our required RPM. So we'll solve that by doing 12 divided by 3.14 and then divided by 4/12. We get that RPM is 11.465. I'm going to leave it to a couple extra digits because we're going to use it for more calculations. If that were a final answer, I'd probably round it to 11.5. But we're going to leave it out to a few digits so we can reuse it and not have round off errors. Next step is to find the required torque. Torque, if you remember, was that 5252 times the horsepower. Oops, I'm getting ahead of myself. That's the engine torque. We want just the torque from the pulley. So the torque here is going to be the load times the length of the arm. So that'll be the 900 times 2. 4-inch diameter, it's 2-inch radius. Of course, we put that over 12 to convert it into feet. So 900 times 2 divided by 12 gives us 150 pound-feet of torque. Next, then we use that torque in the torque formula to find horsepower. So remember, the torque formula is the torque is equal to 5252 times the horsepower over the RPM. So we have the 150 pound-feet of torque equals 5252 times our horsepower is what we're trying to find over that RPM of 11.465. So to solve this, we start with the 150 here. How do we get rid of the 11.465 on this side? Yep, we multiply by it. It's being divided, so we multiply by 11.465. Then how do we get rid of the 5252? Divide. 5,252. We get 0.327 horsepower. So we'd probably round up to a half horsepower motor. Any questions on that one? Okay, so now the next part of this goes into measurement. And what I'm going to do is I'm just going to leave the problems that are on there for you to look at. We're going to switch over to a PowerPoint. See what I have for time. I got 9 minutes. Never mind. We'll just look at what's on here.
On this copy, you can't actually, I can see it on your screen.
Yeah, I can see it's tough on the photocopy to see it. Yeah. So what I really want to go over is just how to make sure you see the appropriate scale. When we're looking at these, anytime you're looking at any sort of analog scale, a lot of your meters are now digital, except for in manufacturing, you have it's kind of a quirk. It's much faster to read an analog meter, especially if you have a go, no-go situation. You guys talked about no-go, no-go. Either it's acceptable or it's not. Even if you're dealing with a needle gauge, if you have a digital readout, you have to stop and think if that number's in the range. If you have a digital gauge, you can just do something to the surface of the gauge, and if the needle is in that colored range, you know that it's acceptable. So it's a very quick read. So in manufacturing, we do still use a lot of analog measurement because of that, because of the speed involved. We don't need a precise reading. We just need to know if it's acceptable. But in order to read these analog measurements, we'll start out with rulers. Boy, that second one is really, that's blurry enough to make me dizzy. Sorry about that. Don't look at that one too closely. We have to figure out what each individual space stands for. And to do that, we look at 2 marked spaces. So we'll go from the 4 to the 5. Doesn't matter which 2 you pick as long as they're consecutive. And then we count the number of spaces between them. Here we have 1, 2, 3, 4, 5, 6, 7, 8. And you probably don't have to count all of them out. You can tell when you're halfway. 8 times 8 is 16. There's 16 spaces. So that means each one of those spaces is a 16th of a unit. In this case, it's 16th of an inch. So when we go to read that, we find a marking, a labeled marking, and we can either count up from that marking, or we can count down from one that's above where we're reading at. Here, since this is, get back here, what we're reading is right there. We could count down, but what I know is 16ths. I know halfway is 8, so that's my 8 16ths. 9, 10, 11, 12. That's at 12 16ths, which reduces to 3/4. So that reads 6 3/4 inches. If you get good with these, and hopefully you guys are good with tape measures, I'm not trying to insult you, but I've got a lot of students that come through here that couldn't read a tape measure to save their life. It's bad. Everybody's pointing fingers at different people in the room. So once you get good with a tape measure, you start to learn that the different size markings. So like here, since this was on one of the larger markings, I wouldn't bother dealing with the 16ths. That's the larger marking. There are 4 of those. So those are quarters. I can just count 1, 2, 3, and I know it's 3/4. So rather than having to count up the 16ths and reduce, you can go off of the size of the markings. Different types of rulers have different types of markings. This is a centimeter ruler. Typically, any metric is going to be divided up either in tenths or hundreds. So it's relatively quick to see. So here, this is going to be tenths. Wow, that is blurry. I'm sorry. You know this is halfway. That's 5 tenths, 6 and 7. That's 3.7 centimeters. This one here, what is each marking on this one? It's an 1/8. Good. So this would be 4/8 or 1/2. That would be 5/8. Are we closer to the 5 or the 6? Closer to the 5. So that's 2 5/8 inches. I get this question a lot. Well, since it's really close to halfway between 5/8 and 3/4, can I call that 11/16? The answer is no. Because if I call that 11/16, you're telling whoever else is reading that measurement that your ruler was capable of measuring to the 16th. It is not. Your ruler is only capable of going to the 8th, so you have to measure to the 8th. That's an engineering thing, and I get very uptight about that. It is really tempting since it does look like it's really close to halfway, but your measuring device does not give you that degree of precision. You've got to report it, the degree of precision of your measuring device. You guys talk about degree of precision and stuff like that at all? No? Degree of precision is just the capability of your measuring device. On a ruler, it's just the smallest division of the ruler. So that would have a degree of precision of an 1/8 inch. What that means is the error is up to half of the degree of precision. So since the smallest division is an 1/8 inch, that means that's plus or minus a 16th of an inch when you measure something. So when you report it as 2 5/8, what you're saying is that's between 2 9/16 inches and 2 11/16 inches. It's somewhere between those two measurements because that's all the precision your measuring device has. We might deal with gauges like this, multi-setting gauges. So first of all, are we reading the small, medium, or large scale here? Medium, because we're set on the 16 for the dial. So our medium scale is this second row of numbers. So again, we have to figure out what the divisions stand for. So we'll pick 2 labeled divisions. This is 11 and 12. There are 10 spaces between them. So that is 1 volt divided by 10. Each space is 0.1 volt. So this is 13, 0.1, 0.2, 0.3, 0.4 volts. If I had the PowerPoint up, I'd have more examples of that. We only have like 3 minutes left. But if this were set to the 24 setting here, to the larger setting, now from 26 to 28, that is 2 volts, There's still 10 spaces, so that is 0.2 volts per space. So this would be 26, 0.2, 0.4, 0.6, 0.8. So you have to make sure you're very careful with that. This one's pretty easy. What's that one reading? Careful. 6.4. This is actually the 7 here because it jumps from 6 to 8. So each of those is 0.2. Have you guys done any surface deviation gauges yet? Yes? So you have the grades that go the same meter will go positive or negative? Yep. So this one's reading positive. Of course, we start down here. What's that telling us? It's gone around at least one. It's gone around once and not quite twice. So that's 1 full millimeter. This is 50, 60, 70, 1, 2, 3, 4. So 1.74 millimeters is how far that's deviated, positive. This one's an inch one. The needle has gone this way. So this is deviated negative. This is between 0.8 and 0.9. Do we know if it's past 0.9 yet? It's gone all the way around and it's not quite back to 0, so it's not quite to the 0.9. So it's 0.8. Then 10, 20, 30, 40, 50, 60, 70, not quite to 80, 78. So that's 0.878 inches in the negative direction. Is that similar to what you guys read? Yeah? Okay. Those are a lot of fun with my other students that have never used them before. It takes a couple of days for them to get used to that. Have you guys read calipers and micrometers? So first of all, can you tell me if this is an inch micrometer or a millimeter micrometer? Tell right here. It goes up to 25. 25 is back to 0, right? That means this is an inch. Also, the fact that this goes in ones, those are tenths of an inch. So this is 0.5 inches is what that is saying. These are quarters or 25 thousandths. That's 25, 50, 75 thousandths. Then this is almost back to the 1. That's 21, 2, 3, 4, 24 thousandths. So 0.599 inches. Calipers. You read the whole inches and the tenths off the main scale here. This is 4 whole inches. How many tenths? Hasn't quite made it to the 5 yet, so it's going to have to be the 4. And then this is at 43 on the dial. So 4.43 inches is what that is reading. This caliper is in millimeters. The joy of metric calipers is even though it's reading in millimeters here, this is actually 1 centimeter. So you have to make that 10 millimeters. That's 10, 20, 25, 6, 7, 27, 60. The tough part about calipers and micrometers when you go from metric to standard is the decimal points in a different spot. So remembering where your decimal point goes. Like here, this is a metric or a millimeter micrometer because it's labeled in 5s here, and also it goes up to 50 before it wraps back to 0. So this is 20. This would be 20.5, 20.1. Do we know whether we've passed that line or we're just about to it? This is 0, and we've just passed 0, which means we have just passed a line. So you can always use the thimble to tell if you've passed the line or not. So it is 21, and that is lined up with the 5. Those are hundredths. That is 0.05. So that's 21.05 millimeters. Well, I've used up my time, actually 2 minutes extra. So